Hello, this is Abhishek Gade, and today we are going to learn about shear strain. So see, this is a bar, okay? This is the bar, and what is happening is we are pulling it from both the sides. So we are starting with the basics and then we'll go on complicating the things, but it won't be so complicated that you won't understand, okay? So the bar is pulled from both the sides, right? So what is happening? There is elongation on this side and there is a contraction in this side. Okay, so in one direction there is elongation and in one direction there is contraction. So tell me, do you feel, is the shape changing? No, the shape is not changing, but the volume is obviously changing. And to get the idea of how it changes, you need to know the Poisson's ratio. Okay, so next, so see, this is the normal stress, but are we normal? Do the activities we do full day, are they normal? Are the forces which we exert are normal? No, we are not normal, as well as the forces we exert are not normal. That's why there is a force called as shear force which we exert. Okay, so because of that shear force, shear stress is going to get come into picture, right? So let's understand first what is shear stress. Okay, so say this is a again a block, and the block is fixed at the end. Okay, so the force is applied over its one plane, okay, which is at the top. Okay, so here, so see, all the planes there would be some slipping, all the parallel planes they are going to have slipping. So how can we define this shear stress? We can define it as the force, the resistance due to force, which tends to cause the deformation by the slipping of this parallel planes. Okay, so that is how we can define them. Now moving on to the actual part. Okay, so someone asks you in interview that, tell me, how will you explain me shear strain? Okay, so now we are going to do that. So see, there is a undeformed body, and then we are deforming it, and this is the shape. So let's concentrate first on the undeformed body. So see, there are two line segments, AB and AC. Okay, two line segments are there, AB and AC, and both are perpendicular to each other. Now let us take this axis X along AB as well as Y along AC. You will ask me why you are taking 90-degree only. I want to take 30-degree, 120-degree. Tell me, you want to know something changing with some reference. Will you take 120 or 30 or 60, or will you take 90-degree? Obviously 90-degree, because that is the best thing we can do, because the axes are also aligned at 90-degree, X and Y axis. So what we'll do is, now let's deform it. Okay, so see, this is the deformed body. Now what has happened? This 90-degree, the A has shifted to A dash. See, and the A, okay, the A has shifted to A dash, and then the B dash and C dash are also shifted, and the angle between now A dash B dash and A dash C dash is theta dash. So it is not 90-degree now, it is theta dash. So something has changed. What? Has the volume changed? Has the volume changed? No. Has the shape changed? Yes. See, you can obviously see the shape has changed. Okay. Shear strain is there now because the angle has changed. Okay. So let's move. Okay. So how will you define shear strain? It is pi by 2 minus theta dash if we consider it in radians. Okay, or you can say it as 90 minus theta dash if we consider it in degrees. Why this 90 minus theta dash? To understand this, again move to the previous slide. Okay, so see, First it was 90 degree, then theta dash. So how much angle changed? Remember one thing, very important line. Not only one line segment is contributing to the angle change, both the line segments are contributing to this angle change. So 90 to theta dash, okay. So A dash C dash has also changed its position, and A dash B dash is also changed as its position. First it was 90, then theta dash. What is the change? 90 minus theta dash. So that's how we got the formula for shear strain. Okay, so let's move. Okay, so shear strain, what can we call it in some words if someone asks? Okay, so that is the, we'll draw this body and tell him it is the change in the angle between two line segments. When force is applied and the body deforms, its shape changes. Okay, so next, so see, there is some convention to be followed. Let's understand what is this convention. First, the line segments, between the two line segments the angle is 90 degree, both the cases. But in one case, after the shape changed, the angle between these two line segments was less than 90 degree. That means shear strain is positive. But if it is greater than 90 degree, then we call it as shear strain is negative. This is just a convention. You can follow the other side also, okay, but still the books follow this, so that's why I'm telling you about this. Next, so two lines for normal strain and shear strain. What is normal strain? It is the change in the volume. And what is the shear strain? It is the change in the shape. Okay, next, so let's move on to some numericals, the interesting part of this session. Okay, so see, A, B, C, D is a square. And now I'm elongating such that, see, A is shifting up above y-axis. See, x and y-axis I am defining so that I can relate it. Okay, so I can relate the dimensions with it. You need to define x and y-axis if you do not understand directly how to proceed. Okay, so see, this A is will shift somewhere up, that you can see using the dotted lines. You can see the dotted lines. Okay, so A and C is shifted outwards and B and D is shifted inwards. Tell me what will be the, only consider this A, B and center part. Okay, consider this as O. I haven't written there, but consider it as O. So A, O, B. Okay, so consider this triangle and then A dash, O, B dash. Do you understand what I'm where A dash will come? I'm telling you the new coordinates, okay, for that dotted line. So consider that A dash, O, B dash. Okay, so tell me, A dash till O. O is this point. See the red dot. Okay. So A dash to O. A dash is somewhere here. Okay. Up. So A dash to O. What will be the new length? It will be A plus C, because see, C amount is changing here. And what would be O to B dash? What it would be? So it would be A minus B, because see, this total is A, but then some, it is going inward by B, so A minus B. So this is how the we need to proceed. Okay, so next, so see, the same thing I have showed you here in the form of a diagram. Okay, A dash, B dash and O. So this is theta dash by 2. Finally we need to know the angle only, because shear strain, so we need to know the angle only, and this is phi dash by 2. Okay, so this is A plus C and this is A minus B. I told you already. So now tan theta dash by 2. Okay, in shear strain, the most important thing you should know is tan theta. Simple. You should know only the tan theta formula, opposite upon adjacent. So what would be tan theta dash by 2? It would be A minus B divided by A plus C. And what would be tan phi dash by 2? It would be opposite, A plus C divided by A minus B. See here. Okay, so from this we'll get theta dash and from this we'll get phi. And simply, what was our formula for shear strain? Pi by 2 minus theta dash. Remember, this is for half angle only. we had a square, so four sides. Okay, so this angle would be double, so that's why I took half here in tan theta dash by 2. Okay, so we'll move on to the next part. Again, there is some square rubber or plate, I don't know, we can call anything. Okay, so this is nth and this is m. These are dimensions, I did not need to mention it. This is b, this is a, this is theta 2 and this is theta 1, and they're asking us find the shear strain. Do you know tan theta is going to become theta? Why tan theta becomes theta? Can you tell me why tan theta becomes theta? See, this is a small angle approximation. Do you know Maclaurin series? So Maclaurin series, what does it say? So tan theta, what is the expansion of tan theta? Tell me. So it is tan theta equal to theta plus theta cube by 3 plus 2 upon 15 theta cube plus dot dot dot. So tell some points. Okay, so for small angle, the higher x cube, x raised to 5, that could be neglected. Do you know tan theta can become equal to theta for angles less than 10 degrees? Okay, so that's why here the angles are very small. That is what mentioned in this question. Or there is no question of, I am telling you, yeah, because you need to assume that to solve shear strain things. Okay, so tan theta would be theta dash. So tan theta, see the triangle b upon ab. Okay, and here it is a upon what this is ad. Okay, so we found theta 1 and theta 2 just using these two triangles. One of this is this and one is this, so two triangles. Obviously, now what is my shear strain? The total change. Okay, so at point A I need to find the shear strain. So it would be, okay, this one thing is changing, the two thing is changing. Add both the thetas, because at point A both the thetas are contributing. Do not forget this. Don't only don't only say that theta 1 is your shear strain or theta 2 is, but addition of both the angles, because the line segments have changed. See, the two line segments have changed by theta 1 plus theta 2. So your answer would be theta 1 plus theta 2. Okay, so moving on next. Okay, so this is what okay, so that was only for A, this was only for A, but now I am asking you, like, what for B, C and D? What for them? What is the shear strain for them? Same. The answer is same. See, here it is. I'll show you using a highlighter. So here it is theta 1. Here also it would be theta 1. Why adjacent? Okay. So because I am drawing a line parallel to this line. Okay. So I am drawing a line parallel to this x axis. So that this will be also theta 1. Okay. Similarly, here theta 2, this is also going to theta 2. Again, if I draw here line, this is also going to be theta 2. Again, if I draw this line parallel to y-axis, okay, I'm drawing it parallel to y-axis, this line, again, this will be theta 2. Okay, this x-axis parallel to x-axis, this will be theta 1. This again adjacent theta 1. So see, everything is now you can see clearly. So this line segment has changed by theta 1 and theta 2 at d dash theta 1 plus theta 2, at c dash also theta 1 plus theta 2, at b dash also theta 1 plus theta 2, and a to we already know theta 1 plus theta 2. See, simple. So shear strain at all the points would be theta 1 plus theta 2, whatever was our answer previously, the same thing. Okay, moving on to the next part. So before beginning, we must know what is the cosine rule as well as the sine rule. So cosine rule, what is the cosine rule? It is, okay, so we know three sides and we know angle for one side. For one angle of the triangle, we know that. Okay, so this is the angle we know. These are the three sides. So what is the formula? A square equal to b square plus c square minus 2bc cos theta. Why I'm telling you all these formulas? These formulas are going to help you to find the normal strain as well as shear strain. Remember, these formulas are the key. Okay, so say, so a square equal to b square plus c square minus 2bc cos theta. Remember this formula. We are just going to use it in some time. Okay, and sine rule is very simple. A by sine A equal to B by sine B equal to C by sine C. Very simple. Nothing to mention in that because we use it generally many a times. Okay, so this is sine rule and this is cosine rule. This you should know to solve further problems. Okay, so let's move on to the next. Okay, so this is one rectangular. Okay, there is a rectangular plate or something, whatever you call it, and then we are stretching it. See, we are stretching it in this direction, in the x direction or whatever direction you call. We are stretching, and so a dash is formed. See, a is there, a dash is here, and c is above. Draw the triangle. We want to know what is the angular change. So we want to know theta here. See this theta. And then if we know 2 theta, then obviously this previously it was 90 degrees. See the diagram, 45 plus 45, it was 90 degree. If we know this 2 theta, 90 minus 2 theta will give us the answer. But problem is where, how to get this theta? Because already we know what they've given. Horizontal displacement x is given, so displacement of a to a dash, that is x, is given, as well as the length AC and AB, the length L is given. Okay, so AC and AB length L is given. Okay, so see ACL, but a dash C, do you know the changed length L? Do you know that? No. So that we will find using cosine rule. See, L dash equal to L square plus x square. X we know it is the horizontal displacement, minus 2xl cos 135 degree. Where did this 135 came? Obviously, if this is 45 degree, this part would be 135 degree. Okay, this part would be 135 degree, no? So obviously it is easy. So if from here we are going to get, okay, L dash we are going to get. Now moving on to the sine rule. We know L dash, we know L, we know X, we know all the sides, and we know angle of one part. Okay, so 135 degree we know. Okay, so sine 135 divided by L dash. See, sine 135 is here, L dash is here, so sine 135 divided by L dash equal to this sine theta, and opposite is L, so sine theta by L. Okay, so from here you are going to get what are you going to get? Theta, because that is only the unknown. And once you get theta, 2 theta is the angle, new angle. And so what was the formula? The shear strain was pi by 2 minus 2 theta. Okay, so this was the end of the shear strain thing. So if you like it, just vote. Thank you.